Okay, I want to talk briefly about unit vectors to um, set up gravitation and orbits and all that. So, unit vectors. A unit vector is basically we want to take a vector that goes in some direction, has some magnitude, and scale the vector down so it has a magnitude of 1. So it's just like a little vector that points in the same direction. So we're going to define a hat is like the a unit vector, and a hat has a magnitude 1, and it's in the same direction as our vector A. So this is useful if we have, for example, and I used A here, so I'll go with an example of its acceleration, but it's important to understand this applies to any vector at all. Whether it's got units or not, whether it's a force or a displacement or velocity or magnitude, or sorry, not a magnitude, or an acceleration or a momentum or an impulse or any kind of vector quantity can be scaled into a unit vector that has magnitude of 1 with no units. So to make this clear, let me show you an example, which is let's just say we have our vector A, and that is 3I hat plus 4j hat, and that is in meters per second squared. So that's a vector about like that. Let's say, and there's 1, 2, 3 I hats, and then 1, 2, 2, 3, 4 j hats, something like that. So and so we want to scale this A vector down into an A hat. What we do is we take the magnitude of this A vector. So the magnitude of A is going to equal, we just take this Pythagorean theorem, square root of 3 squared plus 4 squared. And so the magnitude of A is square root of 25, and that's 5. But what's the units on the magnitude? Magnitude has the same units as the basic vector itself. So the magnitude of A is actually 5 meters per second squared. So now to scale this down into a unit vector, we want to divide this by this magnitude. So A hat, which is our unit vector for A, is going to equal this vector A over the magnitude of the vector A. And that's actually a useful definition, or sort of a useful rule to use for finding any unit vector, is that A hat is going to equal the vector A over the magnitude of the vector A. Or if you're using the standard notation where the magnitude of a vector is just a scalar with the same letter as vector, you can just write it like that. And this is useful going in both directions. Sometimes you will want to find an A hat from an A vector, and so you can use this. Sometimes you will have an A hat in equation, and it actually makes more sense to bring this out so you can do some math, because like you might have A handy, but you might not have A hat handy. So, and we'll see that as we get into gravitation. So, here, A hat, so A hat is this A vector divided by the magnitude of the A vector. So let's make that, this is 3I hat. Actually, let me just bring this up here. A is 3I hat plus 4j hat meters per second squared divided by the magnitude of that, which is 5 meters per second squared. And so, I'm sorry, I can't do anything right today. So, let's get rid of that, and then this is A hat here. Pardon me. So A hat is this A vector here, and then divided by the magnitude. So, we just divide through, and because the units are on top and bottom, they cancel out. So it's again important to know that unit vectors have no units. Somewhat ironically, they're called unit vectors, they have no units, but they're called unit vectors because they are 1 unit long. The unit is 1. So what this comes out to is 0.6 I hat, which is 3 divided by 5, plus 0.8. Try that, that's a little better. J hat, and that's our unit vector. So you can imagine this would be like, A hat is a vector that's 1 unit long, points in the same direction as A, and that's useful sometimes for equations. So one thing that's good to remember from this, one useful product of this, is that if we have circular motion, so let me see if I can scroll down just a wee bit and get a little more space here. If we have uniform circular motion, and we have this, say a center there and an object that's, call it, say the radius vector from the center of the object is r hat, and the object goes around in a circle, okay, and it's got a vector, it's got a velocity vector, v vector, and the acceleration is this way. Well, remember we know already that I'll do this. We know already that a equals v squared over r. That's a common thing we know for motion, but we don't know. This is just scalars. This is just magnitudes. This tells us the magnitude of a compared to the magnitude of r and the magnitude of v. But this doesn't tell us. It tells us what it is actually in vector form. So what we want to do is say what direction a is in, and then we can tell. We can give an expression for this like an a vector, right? So which direction does the acceleration go? Well, it goes in the opposite direction of the velocity, or sorry, not the opposite direction. Sorry, the opposite direction of the radius, right? It points in towards the center along the radius. So really what we have is that, let me just fix that off. A hat is negative r hat, right? And using one of our little factoids above, this one here actually, we can say that a hat is just the a, so a hat is just the a vector, right? Divided by its magnitude, which is just lowercase a. And that equals negative r hat. Now, we can take this side, this bit here, and we can find that a hat, or sorry, not a hat, no, the a vector, so we know a vector divided by a is equal to negative r vector, we can say it's equal to negative a, or negative r hat, I'm sorry. Okay, so we can get to here. So let me just I've stumbled over my own tongue about 5 million times, but let me just point out that this thing I'm circling in blue can be used to find this. Obviously, you just multiply by lowercase a, and you're there. And what we do now is we take this and plug in this thing here, right? We take this, plug that in there, and we can get our actual vector equation for circular motion, for uniform circular motion, which is vector a is equal to negative v squared over r times r hat. That is an actual vector form equation for acceleration for uniform motion. So if you actually know your r vector, then you can very easily figure out what your a vector is. Just and in this case, you just know that you calculate the magnitude and it's in the opposite direction. But if you had, for example, so let me give an example where we have. Let's see, let me just cut out some space here. So, an example where we have, let's say, uniform circular motion, like this picture here. We're just going to co-opt this picture, and we're going to say magnitude of its velocity is, I don't know, let's say 6 meters per second. Okay, so we know it's going in a circle 6 meters per second. At this instant, the r vector is, we'll say, I don't know what's a good one. Let's see, 5. Well, let's say 12 I hat plus 5 j hat meters. Okay, so what we want to do is we want to find our a vector. Okay, and so we can take this equation here and use this and say negative v squared over magnitude of r times r hat. Now, we could, if we wanted, just calculate magnitude of r from this. And in fact, magnitude of r is 13. So that's not very hard. But then we'd have to find r hat, and that's kind of annoying. So what we can do is we can take, let's see, what is it? It's, we know that r hat, we know that r hat is the r vector divided by r, right? So instead of doing all this, or instead of finding r hat explicitly, we can just plug this into here and then say that A vector is going to be negative v squared over r times r vector over r hat, over r magnitude, right? So we're plugging this in here. Don't pay more attention to what I write than what I say, because I'm stumbling over my tongue a lot. But what this gets us then is then that this A vector is going to equal negative v squared over r squared times the r vector. And that's actually very easy now, because we just find this magnitude here. We don't even have to take a square root, really. We just have to take, so let's see. So we set our velocity at a magnitude 6. So negative, I'm just going to go with negative 6. So this is our v squared, 6 times 6. And then we're going to divide that by the square. We want to divide that by the square of this r vector here, or the square of the magnitude of this r vector here, which we can really just find through the Pythagorean theorem, right? 12 squared plus 5 squared. Okay, and if we wanted to find the magnitude of r, if this actual r, we would take the square root of this. But since we're squaring it down here, we just leave it out of the square root. So that works out nice and conveniently for us. And then, unfortunately, this is where I'm going to have to do this in 2 steps. So we have to multiply this once by this I thing, and then once by the j thing, by the j component to find the individual components. So this should give our I component of acceleration. So A equals, and let's see, what was it? Negative 2.56, negative 2.56 I hat. Put the parentheses in there. And let's try it with 5. And negative 1.07, okay, minus 1.07 j hat meters per second squared. And so right there, we've got that's our answer. That's our actual vector acceleration there. And you can see, I tried to sort of pick something that reasonably scale. So I said, this is 12, 12 units over, and this is 5 up for r, which it's about right. And then that means that A is pointing back, to the left horizontally and then a bit downward. So it's pointing back along the same line. I think if you took a dot product here, you'd find the cosine between those, or the cosine of the angle is negative 1. But regardless, so that's how it works. That's how you use hat vectors in a nutshell. And we'll be getting into those as we do gravitation, and you'll find they're very useful. But it's nice to know how to flip them back and forth to regular vectors and magnitudes.